Hello, everyone. We are going to go over Chapter 6 in Chem 201, which is all about chirality and handedness of molecules. So we're going to talk about stereochemistry. So let's get started. All right. So organic molecules, or others actually, can have a property called chirality. This is also referred to as handedness, which we are going to describe. It starts with the relationship among isomers. We've already learned about different types of isomers. Remember, when we consider isomers, we consider that isomers are different compounds with the same molecular formula. We could also break just the category of isomers down into two different types. One is constitutional isomers, which we've talked about a lot in these previous chapters. And here I have the same molecular formula, but I actually have different connectivity of the atoms within the molecule. Now we're going to be talking about something called stereoisomerism. This has the same connectivity of the atoms. The difference is a different orientation. I want you to really focus on this. A different orientation of their atoms in space. So I have the same molecular formula, the same connectivity of the atoms. This carbon is connected to two different carbons and a hydrogen. This carbon is connected to an oxygen, a carbon, a hydrogen, and a nitrogen. But they're arranged different spatially, which is a really important distinction and has a lot of ramifications, particularly in biochemistry. Stereoisomers can be separated into optical isomers, which are enantiomers and diastereomers. This is really important. Enantiomers are molecules that have non-superimposable or non-superposable mirror images. So these two molecules are connected different, or are connected the same, right? I have CH3, CH2. This carbon has a hydrogen, an OH, a CH3, and an ethyl group. This is the same connectivity, but the orientation of this hydroxide and these relative groups are going to be different in space. I can also have stereoisomers that are called diastereomers, and these are molecules that are not mirror images. So we're going to be looking at things by spatial orientations in this section. Models are critical here. Please make models in order to see what these relationships entail. Okay, so there are two major classes of isomers. My constitutional or structural isomers, these will actually have different IUPAC names. I'll have the same or different functional groups, and this will have different physical properties and different chemical properties, and that's because they're completely different structures. They have the same formula, but the connectivity is different. I could have different functional groups even. So they're completely different compounds from one another, so their physical properties and chemical properties are going to be different. Now, stereoisomers are different. because they're only different in the way the atoms are oriented in space. So they're going to have identical IUPAC names. Sometimes I'll have to designate cis or trans here, and they're always going to have the same functional groups. Now, they will differ in their spatial orientation, and this orientation, this three-dimensional arrangement in space, is called a configuration. Stereoisomers differ in their configuration. So we're going to have to learn how to determine these configurations so we can tell these stereoisomers apart from one another, because the IUPAC name isn't really going to help us here. So here's some examples. If I have 2-methylpentane and 3-methylpentane, I have the same molecular formula. They're both C6H14. They have different names because they have different connectivity. Here the methyl is connected on the 2-carbon. Here the methyl is connected on the 3-carbon. That means these are constitutional isomers or structural isomers. Let's look at these cyclic structures. Again, we've talked about this just a little bit before. These cyclic structures are going to have the same molecular formula. The name is going to be the same because my root compound is going to be the same. The name is the same because the only difference that occurs between these two molecules is their orientation in space. This one has both methyls on the same side of the ring. This has a methyl on opposite sides of the ring. So I have to change the prefix. But if I didn't designate that spatial orientation, I would have the same identical IUPAC name. So stereomers can be geometric stereoisomers, which I designate by cis or trans, or they can be optical isomers, which is a little bit more difficult, and those would be my enantiomers and my diastereomers. Optical isomers are always chiral, and they exhibit optical activity. We're going to talk about what that means in a little bit. So let's look at the difference between chiral and achiral molecules. Now, everything has a mirror image, but the mirror image that an object has may or may not be superimposable or superposable. What that means is, if they are superimposable, I can stack everything together and then they will become the same object in three-dimensional space. So this molecule or object that is superimposable on its mirror image is said to be achiral or lacking chirality. A molecule or object that is not superimposable on its mirror image is said to be chiral. Now, when we're talking, generally a chiral carbon is a tetrahedral carbon. So it has 4 single bonds, and I have 4 different attachments to those single bonds. So before I go on, I am going to show you what I mean. Here are 2 compounds. These are mirror images of one another. If I look at these guys, I have the white, the purple, the blue, and the yellow. So this is reflecting this. So everybody should be able to see that. This is reflecting this. And no matter how much I try, I cannot make these superimposable. I cannot get these atoms to align no matter what I do. Two of them are always out of position. This is non-superimposable. No matter what I do, I cannot make anything, the white atom align with the white atom, the purple align with the purple, the yellow align with the yellow, and the blue align with the blue. This is impossible because these are stereoisomers. Notice I have a carbon that has 4 different connections, a blue, a purple, a yellow, and a white. My mirror image is the same connectivity. I have a blue, a purple, a yellow, and a white, but I cannot superimpose them. I cannot get all of these atoms to align correctly no matter what I do with this. So a chiral carbon with 4 different connections, 4 different groups bonded to it, that is going to be a, this is a pair of enantiomers. This is a mirror image, but it is not superposable on one another. Now, let's look at this guy. Here I have another set of molecules. Here I have a mirror image, right? Purple reflects purple, white reflects white, blue reflects blue. My whites are in the back. This is a mirror image. So these 2 compounds are mirror images of each other. But I can just simply put this over this. And now I've got purple connected to purple, white over white, white over white, blue over blue. These are actually the same compound. And notice the difference. I have 2 of the same attachments, 2 white beads to the carbon, and then I have a blue and a purple. So this attachment does not have 4 individual separate groups or atoms attached to this carbon, right? They are superposable. These are mirror images. This reflects this, but they are the same molecule. They are achiral because they can perfectly superimpose. Again, these guys aren't like that. If I have 4 groups attached to the same carbon, there is nothing I can do to get them to superimpose on one another. This is a set of enantiomers because I have a chiral compound that has a mirror image that is not superimposable. Hopefully that helps. Hopefully that also indicates that you really need to use models for this section as well. Okay. So I have isomers. If I have the same connectivity, I'm going to have stereoisomers. If I have no stereocenters, so this is no chiral carbon, it's going to be achiral. This could be cis and trans isomers or geometric isomers. Or I could have stereoisomers with stereocenters. This is going to give me those chiral compounds, which will be enantiomers and diastereomers. What I showed you on the screen was a pair of enantiomers, right? If I have different connectivity, in that stuff we learned in chapter 3 and 4, where I have constitutional isomerism. So think about this. Handedness comes in when we describe chirality. because your hands are actually mirror images of each other, but they are not identical or superimposable, right? You have a left hand and a right hand. I can no way make my left hand completely superimpose on my right hand. In fact, think about gloves. I have to have a right and a left glove. My right hand glove will not fit on my left hand unless I turn it over and make it into something it's not, right? So this is handedness or chirality. If my mirror image is not superimposable on its mirror image, it is said to be chiral. There are many examples in nature about chiral species, and one of the discussion points is to actually try to identify various things around you that exhibit this chirality or this handedness. Now back to chemistry, enantiomers are non-superposable or non-superimposable mirror images. Here is a compound. Here's my carbon. That is what I'm determining if that carbon is chiral. I have an OH, an H, an ethyl, and a methyl. So 4 different groups, an OH, an H, an ethyl, and a methyl. If I draw this mirror plane here, this is reflecting, this hydrogen in the back is reflecting, the ethyl in the front is reflecting, and then the methyl in the back is reflecting. So this and this are mirror images. In terms of models, this is what they look like, right? So these are a pair of enantiomers. This is 2-butanol. I have different spatial imaging here. I have different spatial arrangements. They are actually different compounds because of that different arrangement in space. They are 2 stereoisomers. They are enantiomers. One way to see that the mirror image is not superimposable on the original is to rotate the mirror image. Let's say I'm just going to swing this around by 180 degrees, and then I get this. So this hydrogen is moving from the back to the front. This ethyl is moving from the front to the back, and then my CH3 is going from behind to the forward. Now notice this aligns and this aligns, but this is going backwards and this is coming out at you. Notice those hashed wedge says it's going behind the plane of the paper. The hashed wedge to the ethyl here is coming behind, outside at you. Whereas this is going behind the plane of the paper and this is coming out in front of you. So I can align 2 of the groups attached to this carbon, but I cannot get all 4 groups superimposed on one another because they extend in different directions in space. So if I do this and I try to fit one molecule on top of the other so that all the groups and the bonds match exactly, I'm not going to be able to do this. Here my hydrogen is pointing towards me. Here my ethyl is pointing towards me. There's no way I can change this without breaking bonds. So the original molecule in the mirror image are non-superposable, non-superimposable. They're different molecules. Therefore, because this mirror image is not superposable or superimposable, they are called enantiomers. So enantiomers are stereoisomers that are non-superimposable mirror images that are chiral, which is from the Greek meaning chire or hand. This term refers to the relationship between the pairs of objects. They show handedness. The most common cause of enantiomerism in organic molecules is the presence of a tetrahedral carbon with 4 different groups bonded to it. This carbon can be called a stereocenter or a chirality center because that carbon is causing the molecule to be chiral. So it's a chirality center. It's causing that set of compounds to be stereoisomers. So it's also called a stereocenter. If an object and its mirror image are superimposable, they are identical. And they are, so if the mirror image are superposable, they are identical compounds. And then these are achiral compounds. Here's another example. I can draw the mirror image, but now I have 2 methyl groups. So these are the same. I have an OH and an H. The mirror image is here, but if I rotate that, what I'm going to get is something that I can superimpose, right? So I'm going to take this and rotate it where the hydrogen comes to the, goes to the back. This guy comes up here. This guy, or this guy comes up here. Sorry, this guy comes here. And this guy goes there. So I have this new positioning of the atoms. When I look at this, this is superimposable on this. I can align this methyl with this methyl. I can align this OH with this OH. This hydrogen is going backwards, so is this. This methyl is coming forward, so is this. These are identical molecules, right? All the atoms and the bonds of the mirror image fit exactly on the original. So that means they are the same molecule. We're just viewing them from different perspectives. This idea is why it's absolutely critical for you to be able to make models and look at these differences in space. So to summarize, objects that are non-superposable on their mirror image are chiral, and they show handedness. The most common cause of chirality among organic molecules is the presence of a tetrahedral carbon with 4 different groups bonded to it. So I need 4 different groups bonded to it. Notice in the one that we used, I had 2 carbons bonded to that chiral center, but one was an ethyl group that had another carbon and one was a carbon. To look and see if those 4 groups are actually different, I'm going to keep going out. If I see carbon and then another carbon and another carbon, I'm going to go to my first point of difference. If there is no point of difference, they're identical groups and I don't have chirality. The carbon with those 4 different groups is said to be a stereocenter or a chirality center. Objects that are superposable on their mirror images are achiral. And these actually don't have any chirality. So when I have non-superposable or non-superimposable mirror images, these are called enantiomers. Now this is a big important feature. Enantiomers always come in pairs. Where I have one spatial orientation, I always have the other spatial orientation in nature, unless I resolve them. When I draw these isomers, you have to be able to make sure that you understand how they relate in space. So these are 4 different representations, different perspectives. Each one of these is just one of the enantiomers. Both 1 and 2 show all groups bonded to the stereo center and also show the tetrahedral geometry with the dotted and the hashed wedges. 3 is a more abbreviated line angle formula, although I show the hydrogen atom on the stereo center. We don't normally do that. 4 is the most abbreviated. It's saying that this is coming out, sticking out at me. But what I don't see is that hydrogen that's going behind the plane. Honestly, the best way to show this is to make a model of this and then rotate it around and convince yourself that all 3 of these are the same enantiomer. If they're different representations of this particular enantiomer of 2-butanol. And I can get the other enantiomer by switching 2 of the groups on the chiral center. If I take off the OH and the H and switch them. So now if I make this one hashed and this one bolded, I just made the other enantiomer of 2-butanol. So here I have 1 enantiomer of 2-butanol. This is the other enantiomer. And you need to be able to convince yourself that these are alternative representations of the mirror image. If I look at this guy and this guy, I have the hydrogen going back, and I have this is mirror imaging, this is mirror imaging, the ethyl and the ethyl is a mirror image, and then the methyl and the methyl is a mirror image. This is like the direct mirror image of this enantiomer. This guy is if I took this and swung it around. So now notice the difference, and I'll try to use a different color. This, oops, I need to do that. This is now on the same side. This is on the same side. But notice the difference here. This OH is bolded coming out at me, and this is hashed going back at me. So even though this one and this one are in the same position, the OH is spatially oriented differently. This is going out at me. This is going behind me. This and this are also representative of an enantiomeric pair. Again, it's really critical to make the models in order to show this. You also have to be able to designate a chiral center. We use an asterisk in order to designate a chiral center. Basically, what I'm looking for is a tetrahedral carbon that has 4 different groups. If I look at this carbon, I have a chlorine, I have a methyl, I have a hydrogen, and I have an ethyl. 4 different groups. This carbon here is the stereo center. If I look at this, none of these carbons are stereocentered because they're not tetrahedral. This has got 3 hydrogens, so that's the same group. This nitrogen is not considered a stereocenter. It's only this guy, this carbon here, that is a stereocenter because it has 1 NH2 group, it has a hydrogen, it has a methyl, and it has this phenyl group. So both of these have 4 different attachments to my tetrahedral carbon. And that's going to be designated with this asterisk. There are many examples of enantiomers, and stereochemistry plays a huge role in determining the properties and reactions of organic chemistry. For example, caraway seed versus spearmint is only different in the orientation of space around that carbon. These are non-superimposable mirror images. They are enantiomers. But if you've ever tasted spearmint or caraway seed, you note that they have much different flavors. They are different compounds. They bind with different receptors in your taste buds, and they produce different tastes in your brain. Now, this is true for many drugs. Ketamine is one such example. Here's my chiral center. These are non-superimposable mirror images, right? If I draw this line here, you can see how they're mirror images. These are enantiomers. Just this three-dimensional change in orientation. S-ketamine, which is designating this particular spatial orientation, acts as an anesthetic. The R, which is this particular orientation in space, acts as a hallucinogen. So this is pretty serious. Many of these examples of enantiomers in biochemistry can be extremely drastic. One enantiomer can provide some sort of huge biological benefit, and the other enantiomer can kill you. So this has really huge ramifications in terms of properties and reactions of organic molecules. Enzymes, which are chiral themselves, which if you take biochemistry, you're going to learn about. These are capable of distinguishing between isomers. So let's look at this, R minus epinephrine, which is the natural epinephrine shown in your, or produced in your body. This actually has 3 pockets in the active site of this enzyme, which is tailor-made to bond to this specific enantiomer that has this specific spatial orientation. When it binds, there's a pocket that perfectly fits this group up here. There's a pocket that perfectly fits this OH group because it's partial positive in there, right? It wants to bond with the partial negative on the oxygen. These are partial negatives in this oxygen. This pocket, it's not just sterics where it fits, it's also charges. This pocket is partial negative. Not only is it fit exactly that 3-atom branch, but it's partial negative, which helps stabilize that partial positive. This enzyme is designed for this particular enantiomer. If I have the other enantiomer, which is the unnatural epinephrine, I don't have the same fit. I don't have the same charge compatibility. This is no good. It does not fit into the enzyme's active site. So for those of you who are taking biochemistry, this idea of stereoisomerism is huge in biochemistry. We will stop here, and the next time we talk, we will talk about how I get these R and these S designations and how I use them in nomenclature in order to differentiate between 2 particular enantiomers. So right now, I am going to say goodbye, and I will see you soon to continue our journey into stereochemistry.